Hi there people, welcome back to the Formulaic Approach channel. In this video we are going to be covering the concept of sound waves. Now stick with me to the end of the video because the video is going to be a little bit long but also very educative, and of course it's going to prepare you for your JAMB, your WIEC, and I promise you by the end of this video you're going to gain value. So do what to subscribe to the channel. Now, sound wave, like every other wave, requires a medium for production. So sound wave is produced by a medium, but sound wave is such wave that requires medium, that requires vibrating systems for production. So it means that it is vibrating bodies that create what? Sound waves. Is that okay? So now what's type of wave is sound wave. Now we have two types of wave basically. We have the I've given that classification in my former video, so you can look. I'm going to link the video in the description. But of course, sound wave is in one of the categories that we call the mechanical wave, and that is because sound wave must travel through a medium. Sound wave requires material medium for propagation, hence it is called a mechanical wave. The other type of wave that do not require material medium for propagation are the electromagnetic wave. But these guys, the sound waves, require material medium. That is, they travel through a medium. So in fact, they are called pressure waves because they send pressure down the body of that, down that system, down that body or the material medium through which they are propagated. So they require material medium for propagation, hence we call them mechanical waves. Now, sound waves, like every other wave, also have all these characteristics I also always mention, except one, although that we're going to be talking about, which is the fact that sound wave is longitudinal, and because of which it cannot be polarized. So when we get there, we're going to talk about that. So another thing is that sound wave is also longitudinal. Sound wave is a longitudinal wave. Now, what is a longitudinal wave? A longitudinal wave is one in which the wave will travel in the direction of the source producing it. That is, when the wave is produced at the source, it will go in that direction in which the vibration is set. Unlike water waves, for example, if I have a pool of water here, this is a pool of water in a container, and I throw stone inside. Okay, no, let's put a resting water now, a resting water surface here. So if I send, so my water is resting here, is that okay? Meniscus. Now, if I throw stone inside here, let's say for example I throw stone here. The moment my stone gets into water, or I throw something that cannot even sink, let's say something that cannot sink. Now that thing, when it gets into water, for a while it's going to move up, it's going to move down and up, down and up. So as this guy moves up and down like this, the vibration that is creating is going to create water waves, is that okay? And the vibration that is creating it is going up and down, vertical axis. But what you will see is a ripple system on the water that goes like this. So what do you see? The wave is traveling transversely, so it's traveling in a direction that is perpendicular to the vibration that is producing it. So this is a water wave, we call it a transverse wave. Unlike the sound wave, that when it's produced, it will travel in a direction that is just, that is in the direction in which it is set in motion. It will travel in a direction that is longitudinal or directly in front of the source that is producing it. So for example, if someone makes a sound now, for example, someone makes a sound. So this is a person's mouth, creates sound. All right, so this person shouts, for example. So this person shouts, for example, what you are going to notice is pulsations. So this wave is going to travel in the direction that is parallel to the source of its production. So that is a longitudinal wave. Now, so just like every other wave, we said that for this kind of wave, which is the pressure wave, is going to have points of compressions or high pressure points and low pressure points. So of course, so what that means is that the moment this side, the sound comes out, the air, that is the material medium for propagation of air in this space, in the atmosphere, is the air. Is that okay? So air is material, is that okay? So the air closest to the mouth at that time is set in motion, or is set under pressure, and as that air is pressurized, the next zone there, the next layer of air is not pressurized yet. Is that okay? Now this, I'm just trying to, make bring. This is what happens that makes sound to be heard. Is that okay? So then, after a while, this vibration or this pressure is sent to this neighboring zone, and that zone also becomes what? Pressurized. So by the time it becomes pressurized, the next zone at that time is not pressurized at all. There is diffuse, so we call high pressure and diffuse zone. So after a while, the next time this guy will be sent here again, and then it creates high pressure again. Now this thing happened in microseconds, or even very speedily. Is that okay? I'm just trying to show you so I can envisage what is actually happening that makes that sound to be sent, or how the sound gets into our ear. So by the time it gets transferred like that, high pressure and low pressure zones get transferred like that onto the ear, then it vibrates the ear ossicles, and then to the cochlear and the cochlear nerve, and then that gets sent to the brain, and then it interprets what you are hearing, whether it's the sound of a bell or the sound of your phone ringing. So, and this we know that is in concomitance with the waveform that we normally represent waving. So you see that this guy is the point of minimum displacement. We call this side rarefaction, we call this side compression. I have covered that before. Just want to show you this compression, this rarefaction, this compression, rarefaction. So high pressure zones are the crests, is that okay? While low pressure zones are the troughs. All right. So now, what are the properties of sound waves? Of course, sound wave has the common property of every other wave, which are what? Number one, reflection. So sound waves can be reflected. Now, what is reflection of sound? Reflection of sound, or reflection as with every other wave, is the change in direction of sound or bounce back of sound when it strikes an obstacle, or bounce back of the wave when it strikes an obstacle that is impenetrable. So if the wave cannot penetrate, it strikes the obstacle and hits it, and gets reflected or bounces back its path. So what happens is that, for example, so for a sound wave, when the wave hits an obstacle, it travels back. Is that okay? The wave travels back when it hits the obstacle that it cannot penetrate. So that's reflection of sound. And one of the consequences of reflection of sound is what we call echo. Echo. So we define echo as a bounce back sound. If you don't know what echo is simply the sound you hear when an after effect sound. What I mean is that when you are in an enclosed area, in an enclosure, if you make sound and there is no air penetrating, if you make sound, you are likely to hear your voice later after. So you hear something like me, talking. Do you understand? So that is echo. So now echo, we said, is a bounce back sound. One of the uses of echo is the calculation of the velocity of sound. So this velocity of sound can be calculated when sound is first sent to a particular obstacle, then the obstacle returns the sound, so making the sound to travel in two directions. So it travels the first distance x, travels the second distance x. So total distance traveled by the guy is what? 2x. And recall that speed is equal to total distance traveled over what? Time taken. So when the distance is measured, then we have that this guy is the velocity of sound is going to be what? This is equal to 2x over t, or 2d if you care, whatever you use for your distance, or s, do you understand, or 2s over t. So that is one of the uses of echo. That's one of the uses of echo. Now another good use of echo is in the location of detection of submarines. Detection of submarines. Now, if they want to detect submarines, so what they simply saying is a high-pitched sound, that will come back to them, and because by nature of what they get back, they're able to tell the kind of entity that is inside the water. Is that okay? So that is, the sound wave. Now, I was also mention the speed of sound first. Now, sound travels in air with a speed of about 340 meters per second at room temperature. That is. So 340 meters per second at room temperature, and we are mentioning room temperature because it changes with temperature. So the speed of sound changes with temperature, and in fact the mathematical relationship between them is that speed of sound, velocity of sound, is directly proportional to the square root of temperature. So what that means is that V, for a constant V, V1 over V2, which are velocities, will be equal to root T1 over root T2. So temperature. So this is the mathematical relationship between velocity of sound and temperature. All right. Now, also note that even with this velocity of sound, now one thing you should also know is that though temperature affects velocity, but pressure does not affect the velocity of sound. The pitch of the sound too does not affect the velocity of the sound. All right. So temperature is the major guide that affects the velocity of sound. The amplitude also does not affect the velocity of sound. All right. So, and there are three types of sound actually. We classify sound with respect to the kind of sound that we hear. So, for example, we have the audible sound. Then we have the inaudible sound. There are two types of inaudible sound. We have the infrasonic and the ultrasonic sound. Now, the audible sound is the one that we can perceive, that our ears can perceive, and it ranges between 20 hertz to 20,000 hertz. The sound that we can perceive ranges from 20 to 20,000 hertz. So, while the infrasonic sound has a frequency that is less than 20 hertz, is infrasonic. If you have seen my video in the beginning, I talked about infra. Infra means what? Less or lower, and ultra means higher or hyper. So infrasonic, that is less, lower sound. Anytime you hear the word sonic, sonic means you far, are associated with sound. So for example, you hear sonorous, you understand, sonometer, all those things. So greater than 20,000 hertz, our ears cannot perceive. Do you understand? So some animals use infrasonic sonic sound to communicate, such as elephants. They send very low pitched sounds. You hear me referring to frequency and talking about pitch is because they are related. In fact, the pitch of the sound is dependent on the frequency of the sound. I'm going to get there in a jiffy. So we're just talking about echo. So another use of echo, apart from the detection of submarine, is using sonars. So you see the word son again coming. So it's using sonars. So what are sonars? Sonars are used to detect school of fish. They use them in fishing. They, send down a wave signal, and they're able to tell by analyzing the nature of the wave that is that they get back. They are able to tell what kind of entity is there, maybe a school of fish or a whale or a submarine or something. Do you understand? So that is one other use of sound. Another thing we use sound to do is to determine the depth of sea. So the depth of the sea, what they just basically do is the same thing. They send a wave signal, which is reflected back, and then you get that. So now there is a concept known as reverberation. Reverberation. Now this is one of the disadvantage of echo, and that is reverberation. Reverberation is when there's multiple reflection. Is that okay? So when there's multiple reflection, and reverberation is very is a typical quality of an environment that has poor acoustic property. An environment that has poor acoustic property. So reverberation is bound to occur. All right. And one of the so in order to prevent reverberation, that is why you see in studios. If you've ever been to studios before, you notice that when you're outside the studio, you might not even hear anything, and a live band is performing inside. Is that okay? Because they usually the walls and the ceilings of those places are usually heavily padded. Do you understand? So those heavy paddings allow for the echo to to diffuse, to enter, it absorbs the sound. Do you understand? So that is how to prevent reverberation. Now, having talked about echo, now let's talk about so we've talked about the speed of sound, which we said is 340 meters per second, and you can also test that. If you've ever done this before, if you're in the church, for example, or you're just in a gathering where they are playing music, you can move far away from that place, a little far away, and you'll notice that what you will hear, the way you'll be dancing, if you can see, make sure you can still hear that music. Is that okay? But the way you will dance to it will be different from the way if you can see the people that are dancing. You will see that the way you dance to it will be, your own rhythm will be different from their own rhythm. So that is, a proof of the fact that the speed of sound is very low compared to the speed of light, that you used to see. Is that okay? So we said it changes with temperature. It also changes with density of the material through which it's traveling. So the higher the density of the material, the higher the speed of sound. In fact, in water, the speed of sound is about 1,500 meters per second. While in steel, so this is in water. While in steel, the speed of sound is about 5,000 meters per second. So you see, that is very fast. That is very fast. So that is about speed of sound. Now, one very common experiment that is used to prove the mechanical nature of sound, I forgot to mention that, is the one where we use the bell jar. Is that okay? So there's a bell jar that is connected. So there's a jar and there's a bell in here. What's the bell? There's going to be a node here that's connected to it's going to be connected to an electric component, and that electric component, so by the moment the switch is closed, this thing will begin to hit the bell, and there's a pump, a pump that is connected outward, and the essence of that pump is to drive out air, to suck air out of this jar. So the moment air stops, in fact, as the air is going out, the bell jar, the sound that is heard on the bell jar will reduce. The intensity of sound that is heard will reduce until when the air is finally sucked out, perfectly sucked out, then you will not hear any sound again. No sound will be heard again. All right, so that's it. That's what proves that air requires material medium for sound, rather requires material medium such as air for propagation. All right, now we've talked about reflection of sound, which is a characteristic. Now another thing to talk about is refraction of sound. Let's talk about refraction of sound. One of the consequences of this one is why sound travels faster in the night than in the day. So you've ever heard, you've ever, you know, if you are doing something at night, you have to do it gently. They will say because you are disturbing others, and that's the truth. So it's, even in the night, you'll notice that if say plate breaks in your house, someone in the other flat can hear because of the speed of sound. The speed of sound. Now what happens is this: in the day, the air in this lower atmosphere is, the air will be hotter, while the air in the upper atmosphere will be cool. So what happens is that as you send in sound, since sound travels faster in the cool, in the hotter region, when the air is hot, the speed of sound is faster. So you see that the sound will be reflected up. But in the night time, the air is warmer on top and cooler here. So in the night time, rather, it's reflected upward because the air is warmer on top and cooler in the lower atmosphere. But in the daytime, as you speak, the air is warmer in the lower region and cold hotter in the upper region. So what happens is that air gets refracted down. So if air is refracted down to the earth, then that's one of the reasons why it doesn't travel as fast that much. So that's one of the consequences anyway. Refraction of sound is what reduces the speed of sound in the day, and in the night it increases it. So now another quality of sound that we should talk about is the interference. Now, before we even talk about that, we are supposed to talk about the. Okay, let's talk about interference. Let's talk about interference. There are many things to cover. Let's talk about interference. Now, interference is just when two waves are superimposed. So the principle of superimposition of wave, I've covered that in that video too. But of course, is the interference of sound that leads to what we call creation of beats. Is that okay? Interference of sound leads to beats, and so it's just when a particular wave is traveling at a particular frequency, another wave is traveling at another frequency. By the time they interfere or they are superimposed, the resulting beat, the resulting wave, is something like this, and it's going to have, the same high pressure point and low pressure point. But you see this irregularity is the wave. So we have F1 and F2, frequency 1 and frequency 2 of the two, frequency 1 and frequency 2. This one will be called F sub B, which is the frequency of the beat that is created. So and you get that by saying F2 minus F1. Just subtract the frequency of both from each other, and you get the frequency of the beat that is created. So that's the consequence of interference of sound. Now I've talked about the fact that sound wave cannot be plane polarized. Sound waves cannot be what? Plane polarized. Why? Is because sound wave travels in one direction. That is it is a longitudinal wave. It is not transverse. It is not transverse. You should go and get so as I was saying, I said that sound waves cannot be plane polarized because it is a longitudinal wave. So, and for a wave to be polarizable, the wave has to be a transverse wave. Transverse wave means that it is traveling in a direction that is perpendicular to the plane to distance. It has to be traveling in a direction that is perpendicular to the source that is producing it. All right. So, and of course, There's also the diffraction of sound. Sound can also be diffracted. Sound can also be diffracted. One of the consequences, the Doppler effect, which makes it such that as a sound wave is moving away from a source, it looks as if the frequency is reducing. It's called Doppler effect. It's called what? Doppler effect. So, as sound wave, if a bike passes now, you see that it will look as if the frequency of that sound the pitch of that sound is reducing. You understand what I mean by pitch now? Now let's even talk about that. But that's Doppler effect, by the way. And as the bike is approaching, it will look like the intensity is increasing. Intensity is different from pitch. Intensity is the volume of the sound. Is that okay? Yeah, it's the volume of the sound. And intensity of sound too has an effect. But let's talk about the three major three things we use to describe sound. Three properties we use in describing sound. We use the pitch of sound to describe sound. We use the pitch. Let me just write them here. Let's list them here. We use the pitch of sound to describe sound. We use the intensity of sound. Now we also use the quality of sound. Is that okay? Another for quality of sound is the timbre. Is the what? Timbre or tone of sound. All right. Now, what is the pitch of sound? Now, the pitch of sound is basically the slimness of the sound, or the thinness, that's the word, thinness of the sound. So for example, if a girl speaks now, how do you differentiate? You can differentiate between a girl's voice and a man's voice, right? Why? One is deep, right? So that one that is deep is going to have a low pitch. Is that okay? And now that is thin is going to have a high pitch. Do you understand? So for example, if I have these two waveforms now, look at this. Which of these is the voice of a male and which one is the voice of a female? An adult male. No, this one is the voice of a male because this frequency is lower than this frequency. Do you understand? So this one has a higher frequency now. Do you understand? Right. So thinness of sound. On the musical scale, you know that if you press a key on the keyboard, on the lower end, on this lower end, you see that it will be lower, it will be like than on the upper end, right? On the upper end is going like, right? So this can also refer to, on the musical scale, the position of a key, or of a note rather, the position of a note on the musical scale. So for example, let's quickly do a little bit of music. We have do, re, mi, fa, sol, la, ti, do. Now, so if you go from here, from do to do, what you have is do, do. Do you see that? It is still the same key, but I'm still the same notes, but different pitches. Do you understand? This is the lower pitch. So if I wanted to go back, do, ti, la, so, fa, mi, do. So do, re, mi, fa, sol, la, ti, do, re, mi, fa, sol, la, ti, do, re, mi, fa, sol. Do you understand now? I cannot go for it, but you see this. So these sets, we call them octaves. We call them what? Octaves on the musical note. So the point is, so you see, I was able to go like just two octaves and some. But the point is that as I go and as I proceed like this, my pitch is also what? Increasing. Do you understand? All right. And what pitch, what frequency means is number of revolutions per seconds per time. So it means that my revolution per second is what? Increasing. Now, one of the ways in which they calculate or they measure frequency, is that okay? Is or more like an experiment. They use what they call this disc siren. The disc siren. Is that okay? A disc siren is just a particular plate that has several holes. several holes. So then there's something like a air blower, that this one will be rotating on the shaft. So as it's rotating, there's a air blower that will be creating, will be blowing air into the holes. So the number of this thing that you hear as you are rotating little by little, the sound you hear will be more like, it will be almost equal to the sound of this thing. But the moment this thing rotates speedily, and this faster this thing rotates, the slimmer the sound that you'll be getting. Is that okay? So the frequency of sound is calculated using on this this siren is calculated using the number of revolutions of this siren times how many holes are there, number of what holes, over did you bring your phone? Did you bring phone? Okay. Now over the time over which it's rotates. Then another one we use is two-third wheels. Two-third wheel. So a two-third wheel is simple. Down is a very simple experiment. If you have ever seen what do they call this thing? This thing that rotates gears on baby's toy. You see something like this. Something like this that has like this, right? And it's a rotating shaft, the rotating part of this thing, right? That it causes, one will be connected to the other, will be causing the other to rotate, that kind of thing in your head. So it's a two-third wheel. So let me draw it in a way that it can make more sense. So if I have a circle like this, just make something like this. So it forms a circle like that. So as this thing is also rotating here, they're not going to put a cardboard or something here, or something that will not hinder the rotation. So the number of time, as this is rotating, think of it, if this is rotating, and they put a small flap here, as that flap is hitting, what will you hear? Pa, 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 pa. The moment that thing increases in speed, what will happen? Oh, right? So that is a measure of the frequency of that thing. So F frequency in that one is number of revolutions times what? Number of teeth, yes. Number of teeth that touches it per time. Do you understand now? Right. So that is how we analyze for the pitch of sound. Alright. Now the next thing is intensity. Now intensity of sound is the volume of the sound, or the how intense, intense, right? How strong the sound is, strength of the sound, that is intensity of the sound. So intensity is dependent on the amplitude of the sound. Is that okay? So for example, which of these sound waves has a higher is loudest? Which sound is loudest? A or B sound? B exactly, because what? You see the amplitude is higher. Do you understand that? And like this. Do you get what I'm saying now? So it has a higher amplitude. But looking at it, which one will have a higher frequency? A, right? Because if you look at it, you see that the wavelength of this is here. But this one has finished its own, completed its wavelength around this place. Do you understand? So it's, it has a higher frequency, even though it's not so obvious. Alright, so intensity of sound is denoted by E. Intensity of sound is denoted by what? And it's given by E sub naught over D squared. Now, this E sub naught means intensity of sound at a particular point. Now you can hear the birds chirping, right? The sound we are hearing here, that we can hear here, is not equal to the sound they're actually producing. The sound we are hearing is an inverse squared relationship between the distance and the intensity of sound we can hear. If you climb that tree, will you hear the same level of sound? What will you hear? A higher level. You want it to be louder, right? Good. Intensity is also called loudness of sound. That's what I want to remember. Loudness. So you are going to hear a louder sound because of now the distance has been reduced. Is that okay? So it means that intensity is very dependent on loudness. So you discover that if you move it just a little far away from church, if you are inside church, if you move just a little far away, you see that you might not, what you will hear will be so low than when you are inside the distance, that everything. Of course, the wall also, cause some reflection and all, so sound cannot go out, but even then, the sound actually decreases with increase in distance. Do you understand now? All right. Then E sub naught is the intensity of sound from the source, actually, from the source. And the loudness of sound is measured in the unit called bells. The loudness of sound is measured in units called what? Or intensity of sound is measured in units called bells. So if you have seen your speaker, your mixer, you see 1 dB, 2 dB on the mixer that I use in church. So that dB means decibels. It's a logarithmic scale. Is that okay? But we're not getting into it today. So the unit of intensity of sound is what? Bells. Now, the quality of sound. The quality of sound is what separates it from, what separates different instruments from each other. So the quality of sound okay, so we said the quality of sound or timbre or tone of sound. Now, this is what I said separates different instruments and different musical instruments from each other. Is that okay? So some musical instruments, we have 3 classifications of musical instruments. Is that okay? We have wind instrument, string instrument. How are you doing now? Okay, wind instrument and what? We have wind, string, and percussion. Percussion are drums, the one I play. And anything that has to do with beating something is percussion. Then string are the ones that have to do with, yeah, you understand? Then wind are the ones that has to do with blowing. Is that okay? So keyboard is what? String. You beat it. The string. Yes. So my point is this now, that quality is what differentiates them, or tone, what differentiates sound. So, and this quality depends on a property known as overtone. On what? Overtone. Okay, so before we know overtone, there's something we must also know, which is called harmonics. Harmonics. Alright, so the quality of the sound is dependent on its overtone, but overtone are higher frequencies of the fundamental frequency, and I'm going to put that into context. So let's go. Harmonics and overtone, right? Harmonics. Now you really have to understand. If you have not been paying attention before, pay attention here. It's very, it's quite tricky. Harmonics and overtones. Okay, we mentioned 3 types of instruments. We are going to examine all those instruments except percussion. Is that okay? Now, we'll be observing the string instruments and the wind instrument, or pipes. We call them pipes also. Is that okay? Now, the string instruments, we mentioned them: guitar, violin, and all that. Then wind and the keyboard. Then wind instruments, we have trumpet, which are down. Flute, all those guys. All right. So now let's explain what is called harmonics and overtones. Now we'll now use it in the context of this string and wind instrument. Now harmonics, right? Harmonics are integer multiples. Harmonics are integer multiples of fundamental frequency. Okay, means we must know the fundamental frequency. So what is fundamental frequency? F naught, right? First, the fundamental frequency is the lowest frequency. Fundamental frequency is what? The lowest frequency that can be produced from a musical instrument. So then, what is now harmonics? So harmonics means integer is just multiples of fundamental frequency. Is that okay? So we now have what we call set of harmonics. Is that okay? So set of harmonics, we have our first harmonic is the fundamental frequency. So we have first harmonic, we have second harmonic, we have third harmonic, we have fourth harmonic. Are you getting it? Are you with me? So the same way is just 1 F0, 2 F0, 3 F0, 4 F0. These are integer multiples of the fundamental frequency. Now this only applies to this one I just wrote down, only applies to string, and you're going to see how. But I want you to understand the concept of harmonics. Is that okay? These harmonics are integer multiples of the fundamental frequency. Is that okay? So fundamental frequency times 1 is what? The first harmonic. Is that okay? The fundamental frequency is the first harmonic. The fundamental frequency is the second, 2 times the fundamental frequency is the second harmonic, 3 times that third harmonic. Are you getting it? But we now have overtones. Overtones are higher frequencies than the fundamental frequency. Higher frequencies than the fundamental frequency. So any frequency that is higher than f sub naught is called what? Overtone. Do you understand now? So if this is the fundamental frequency, where is our first overtone? If f naught is equal to fundamental frequency, what's our first overtone? I said any frequency that is higher than the fundamental frequency is called what? Overtone. So if this was our fundamental frequency, where's our first harmonic? Second, our first overtone is the second harmonic. Do you understand now? These are first harmonic, no overtone. So this will be our second harmonic, first, second and third harmonic. Are you getting it now? So frequencies that are higher than the fundamental frequency are called overtones. And I said overtone is what determines the quality of the sound. Now let's now analyze for a string instrument. For a stringed instrument now. So we call it vibration in strings. That's the subtopic. Vibration in strings. And we have 3 types of vibrations. We have free vibration, where there is, free, just like the name implies, just goes in space. Is that okay? Damp vibration. Damp vibration means probably because there is a material medium that is causing it not to be, that is reducing it, that is breaking it. Damp vibration. And there is also forced vibration. So forced vibration is a special type of forced vibration is the resonance. Is that okay? I'm going to show you a video of one man did on resonance. He vibrated a tuning fork. You know a tuning fork, right? You've seen one this that vibrates like this, U-shaped like this. That has prongs. These are called the prongs. So when you hit it here, you've seen it before. It's called a tuning fork. So he set it in motion, and the thing did not vibrate at the frequency of the other one. So that other one did not move. When he put a tuning fork that had the same frequency, that could vibrate at the same frequency as the other one that was. Both as he hit this one, that one also began to vibrate. This thing is because of what? The concept is called resonance. The concept is called what? When one vibrating body causes another vibrating body to vibrate. Do you understand? Because of equanimity in what? Frequency. Because they have equal frequencies. So one guy is setting the other guy to vibrate. So now, vibration in strings now. Now, a string, for example, a guitar, is held at 2 fixed points, isn't it? And it has a length. So from here to here is a particular length, isn't it? Good. Now, listen to me. The fundamental frequency of this thing, we want to analyze the harmonics and fundamental and overtones. Is that okay? So the fundamental frequency of this thing is the lowest frequency that it can get. And where can we get the lowest frequency from this guy? Is when it is fixed at these 2 ends. So as it is fixed at these 2 ends, if you pluck it once, are you in? What you will notice is that it will vibrate. Let's just draw it on it. It will vibrate up and down. Does that make sense? to vibrate up and down. So more like this guy will go up. So it's going to vibrate up and down. The point where it is fixed here is called the node. It's called what? That's the point of no displacement or minimum displacement. No displacement. In fact, think of it that way. Node, no displacement. No displacement. All right. While there is the point of maximum displacement, now it's called the what? The antinode. Maximum displacement. So the antinode is the midpoint of node. If you remember in our beginning of wave, we said wavelength is the distance between three nodes or three antinodes. Okay, so I want you to know how to, get that one. So look at this guy. So this is our antinode. Let's just call it here antinode, here node, here node. Do you get it? So now, what is the wavelength of this thing? What's the wavelength? It's very simple. Just look at it this way. Do you remember that if we want to get one wavelength, we go like this, right? So this is one wavelength, this is one wavelength. This is a full wavelength here. Does that make sense? Let me just clean this one off. Yes, that's a full wavelength. It means that this place will be what? Half wavelength, right? Good. So if it is half wavelength, so what does this correspond to? This one? Okay, let's see. This point of node displacement, node, node, node. Midway, antinode, antinode. Is it clear? Now let me teach you a very simple way to analyze it. If this whole thing, look at it. If from here to here is a wavelength, what would this place be? Half a wavelength. By the way, this is half a wavelength. But let me show you something again. So if this place to this place is half a wavelength, this middle will be what? A quarter wavelength. This will be 3/4 wavelength. Right? Good. So if that's the case, it means that from between a node and an antinode, we always have what? A quarter wavelength. A quarter, a quarter, a quarter. Does that make sense? Good. Let's make sense of that in this place now. So between a node, between one node to an antinode, what do we always have? Quarter wavelength. This one will help you everywhere. So let's see, from here to here, what do we have? Quarter wavelength. From here to here, what do we have? Quarter wavelength. So by the time you now check this, you now add it up, you get the total wavelength. So one quarter will give you what? Half wavelength. Does that make sense now? So the entire length of this string, the entire length is equal to what? Yes, and which is equal to lambda over 2. Does that make sense now? So in the context of calculation, let's say we now want to calculate the speed of sound, the speed. We say V is equal to F lambda. Do you remember the formula in wave? V is equal to F lambda. So what will frequency be? Frequency is equal to what? V over lambda. Does that make sense? Now, so what will be the lowest frequency of this thing? That's what we're analyzing for. And we got it from here, right? The lowest frequency will be called F sub naught, right? So F naught will now be equal to what? V over now. What is lambda? Let's make lambda the subject of formula here. Lambda here will be equal to what? Lambda will be equal to 2 by the time it cross multiply, isn't it? So F sub naught will now be equal to what? V over So that is the fundamental frequency. Is that okay? Okay, now watch this. Look at the second scenario, the second condition. So this fundamental frequency will be called the first what? First harmonic. The fundamental frequency is always the first harmonic. So look at this. There's no overtone. Now look at this one now. If this string, if I put a fixed point here, if I fix this point, more like I hold the string here and now vibrate. This way to vibrate like this and like this. Do you understand now? So this thing also has a length, right? It has a length. Now, what's this? A complete wavelength. God bless you. So length here is equal to what? Lambda. That makes sense, right? So if that's the case, we call that F is equal to V over lambda. So this one will be the second harmonic. So we'll call it F1. We call it what? F1. So this will become V over lambda. And lambda is equal to, here we have said that lambda is equal to L. Is that okay? The convention is we write the guy on this left side. So the answer is equal to what? V over L. Does this make sense to you? First overtone. Let's be arranging it here. So we've gotten our first harmonic. God bless you. That's the first overtone, right? We've gotten our second harmonic, F1. And this guy was V over 2L. And this guy gave us what? V over L. Let's see if we can go further. Yes, we can actually go further. Let's say this same string, I hold it at 2 points now. So if I hold it at this point and this point, what do you see? It's going to vibrate like this, and like this. Isn't it? And this one vibrate like this, and like this. Does that make sense? Good. So how many wavelengths is this? This guy has length 2, of course. So how many wavelengths is this? So let's see. So this is 1, right? And this is half. But if it's still confusing you, just come and do node, antinode, node, antinode, node, antinode, node. Do you understand now? So from here to here, 1 over 4. 1 over 4. So how many 1 over 4 will you have? Let's say 1, 2, 3, 4, 5, 6. So it means that we have 6 1 over 4 lambdas. Does that make sense to you? So this becomes 2 here, 2, 2 here, 3. That becomes what? 3 lambda over 2. You see, it's simple. If you don't know how to look at it, that's what I'm saying. Just calculate it this way. Right. So it means that the entire length of this string is what? 3 lambda over 2. So what will lambda be? Lambda will be equal to 2L over 3. So this is lambda. So what will our F2 now be? Because this is our second overtone or third harmonic. So what would that be? V over lambda is now this, right? Recall that F is equal to V over lambda. So F2 will now be equal to what? V over lambda is this. That will be 2L over 3. Remember that when you are dividing with a fraction, that will be 3V. So F2, let's bring it down here. F2 is equal to what? 3V over 2L. Okay, let's bring that here. So F is equal to, so I've done F2 now. F2 is equal to 3V over 2L. This makes sense, right? Let's go just one more step. One more step. So we still have our string. We now hold it here and here, right? And here. 3 points, right? You guessed the answer just now. That what? 4V over 12. That becomes what? So let's see if you are correct. Alright, so see this. Well, that's what it looks like, right? But let's see. And I know you're correct, but anyways, let's just prove it, eh? For both of the audience. So L, complete length. So how many wavelengths do we have here? 2 wavelengths. 1, 2. If you are not sure, just say node, antinode, node, antinode, node, antinode, node, antinode. That will be about 8, right? Because then it's 6. So that will now be 8 times lambda. That will now be 2 lambda. Does that make sense? So the entire length is 2 lambda. Also, what's lambda? Lambda is L over 2. We're making lambda. We want to know what lambda is here. So I recall that F is equal to V over lambda, right? So F will now be equal to what? V over L over 2. Does that make sense? This guy goes up. F now, this is F3. Is that okay? F3 will now be equal to what? 2V over L. Do you see it now? Alright. So F3, which is our what? Fourth. Is our fourth what? fourth harmonic, but what? Third overtone. So there are three overtones that are produced now, three sets of overtones. So we have 2V over L. If you look at it vividly, if our fundamental frequency is this, does it not look like the other frequencies that are producing are just really integer multiples? As in, so fundamental frequency is V over 2L. To get F1, F1 will be equal to 2 times F naught. Let's see, 2 times, what is F naught? V over 2L. This takes care of this, V over L. The next one, 3 times F naught. 4 times, do you understand now? Alright, so that is, and that is only applicable to strings and open pipes. We are going to see it in a jiffy. Let's quickly do that of pipes now, wind instruments. For what? F4. F4 will be the fifth. That will be 5V over 12. You get it? So, now let's do for wind instrument now. Wind instruments. Now for wind instruments are classified into two. We have open and closed. Open instrument and closed. Is that okay? Now, when you say it is open, or when you say it is closed, it doesn't mean it is closed at both ends, because air has to pass through somewhere. So it is open at one end but closed at the other end. That's meaning of closed instrument. Do you get it? Are you getting it? So now let's start with the close. Maybe we should start with the open. Let's start with the open. So if I have this pipe like this, should we stand it or slant it? Let's slant it. So look at this pipe. The lowest kind of vibration that you can get here, when you send air into this column, the lowest vibration you can get is one that looks like this. Is that okay? Or if we were to stand it, you send air into it, the column will vibrate like this and vibrate like this. Is that okay? It's still the same. So I think I prefer the standing. So what happens? So by the time I send air into this thing and it vibrates like this, what do we have? This thing has a length, right? This thing has a length, right? So how many wavelengths are here? And this is where your antinode and node V become very applicable. Highest displacement, antinode, right? Lowest displacement, node. Are you looking at it? And this one is what? Antinode 2, right? So let's go. From here to here is what? 1 over 4 lambda. From here to here is another 1 over 4 lambda. Does that make sense? So what does this give us altogether? 1 over 2 lambda. So the length of this thing is 1 over 2 lambda. Does it not look like this? Let's continue. So then we have that length is equal to what? Lambda over 2. So that lambda will be equal to what? 2L. And recall that F is V over lambda. So that F sub naught, which is the fundamental frequency of a wind instrument open at both ends, we have F sub naught will go to what? V over, what is lambda? 2L. Very correct. If the fundamental frequency is like this, then it means that other frequencies will just follow suit. Well, let's prove it. Let's prove it. What we'll do is this. Now let me draw some diagrams for you on the board. So maybe you do that one later. Is that okay? Yeah, as well as the audience, try all of these ones that I'm going to draw here. What's complete? No. I just want you to see this. So if this is the fundamental frequency, this will be the first overtone, right? Or second harmonic, right? So the third harmonic, I want to do the third harmonic. If they are alike, if their sequence of harmonics are alike, then the third harmonic should be the same. Do you understand? That's the third harmonic, right? Isn't it? So let's go. The vibration will go like this. Yeah. Are you getting it? Let's all go like this. Ah! See, I drew nonsense. Just manage it. So here, look here now. So what will this place be? This guy has a length too, right? The length of this guy what? L, right? So we have here will be antinode, here node, here antinode, here node, here antinode, this node, this antinode. So let's see how many quarter wavelengths do we have? 1, 2, 3, 4, 5, 6. So that will be 6 times what? Quarter wavelength, isn't it? So we have 2 here, 2, 2 here, 3. So the entire length of this thing is 3 lambda over 2. So the lambda will be equal to 2L over 3. Does that make sense? So F2, which is our, because it's our third frequency, third harmonic. Is that okay? Third harmonic will now be equal to V over, lambda is not that, so that will be 2L over 3. This guy goes up, and we have F2 is equal to what? 3V over 2L, which is exactly the same as this guy. So it means that vibration in an open pipe is the same as vibration in what? In strings. Is that clear? And let's now treat the case of closed pipes. Let's treat the case of closed pipes. So, with closed pipes now. Oh, we're also supposed to talk about the sonometer. We'll talk about the sonometer soon. Sonometer, let me write it somewhere so that I will remember. Sonometer. That is with strings. Is that okay? Vibration in strings. There's something about the sonometer that you should know too. So listen. So with closed pipe, this is a closed pipe, an example of a closed pipe. You see it's closed at only one end, right? The lowest frequency I can send, the lowest vibration that can happen here is the vibration that goes like this. Is that okay? So if this is the lowest, what will this place be? Antinode. So from here to here is a particular length. From here to here is a particular length, right? So the length of this thing, what's the wavelength? 1 over 4 lambda. That makes sense, right? So it means that lambda here will go to what? 4L. Does this make sense? Good. So recall that F equal to V over lambda. So what will be the fundamental frequency of a closed pipe? The fundamental frequency will be equal to what? V over 4L. Is it clear? Is it clear? Now the next one is this. The second kind of wave that we can pass here is this. One that looks like this. Alright. So I'm also going to talk about something about this. The vibration does not usually start from the end. When you send vibration using a tuning fork, for example, I'm going to talk about that. It's called end correction. But just look at this now. So what happens is this. We have this length too. Keep in mind that the length might be the same, but the kind of vibration will pass is what matters. Are you with me now? The length of this thing might be equal to the length of this thing. So the entire length of this thing, how many wavelengths does it cover? Node, antinode, node, antinode. So we have 1, 2, 3. That will be 3 times 1 over 4 lambda. Simply say 3 lambda over 4. Just putting the lambda on top next time. So L is equal to this. So what will lambda be? 4L over 3. This makes sense, right? So what will be our first overtone? What will it be? V over 4L over 3. So F1, F sub 1 will equal to what? 3V over 4L. This is the what? Our second harmonic. Good. Now let's do one last one, which is something like this. You send this kind of wave like this. I drew this somewhere. So look at this one now. We're going to have a node, an antinode, a node, an antinode, a node, an antinode. How many nodes do we have? 3 nodes. 1, 2, 3. How many antinodes? 3 antinodes. 1, 2, 3. So that's a wavelength, isn't it? That's a wavelength. But let's still check. Let's check. We have 1. I'm not looking at the body. 1, 2, 3, 4, 5. So that is 5 times, you see, lambda over 4. You see, we're not so correct. There's no one wavelength. Is that okay? There's no one wavelength because it goes beyond one wavelength, yes. So what do we have here? We have length is equal to what? 5 lambda over 4. So lambda will be equal to what? 4L over 5. So F2, which is the second harmonic, is going to be equal to what? V over 4L over 5. So F sub 2 is equal to what? 5V over 4L. Don't write again, just be listening. We're going to recreate everything for me. Is that okay? Alright. So now let's now create our sequence of harmonics. Harmony in a vibrating string like this. Let's see what the harmonics we're able to create. So in an open pipe, the set of harmonics will be what? F0, F1, F2. Does that make sense? So what's F1? V over 4L. Second harmonic, 3V over 4L. The third harmonic, 5V over 4L. What does it look like to you? The first harmonic here is 4V over, the first harmonic here, 4V over 4L. The second harmonic is just 3 times F0. Does that make sense? 3 times this will give this, isn't it? The fourth one is just 5 times F0. What would the third overtone be? 7 F0. You have not seen it. But can you see it in the calculation? That's what I'm saying. 3 times this will give you 3V over 4L. 5 times this will give you 5V over 4L. Alright, so that's the case with the harmonic. So how can we generate an equation like that? Since this place, so if I say your set of overtones will be equal to what? The set of overtones will be, if I say first overtone, this is our first overtone, right? That will be 1 plus 2 is 3F0, right? Your second overtone, that is 1 plus, I think it's 1 plus 2N. So here 1 plus 2N. So that is second overtone, first overtone, second overtone. 1 plus 2N because, so 2 times 2, 4 plus 1 is what? 5F0. Is that okay? Your third overtone because what? 1 plus 2N also. 2N is now 3, right? Do you see now? You see maths is 4, right? This is what we just did. So it means that for our overtone, the general formula will be what? 1 plus 2N times F0. Does that make sense? Do you understand? Alright, that's that. Good. Now let's quickly consider the sonometer. Now a sonometer bridge is used to measure the frequency of wave on a meter long a meter long string, pick your note, on a meter long string, we want to determine the frequency. So that's why it's called sonometer, like sound meter. Do you get it? All right. So I said anything you hear sono, so it has to do with sound. Is that okay? All right. So a sonometer looks something like this, and you have fixed points around here, and you set a wire here, and you put a weight. Is that okay? With experiment on the sonometer, it is found that the fundamental frequency of a spring or frequency of a string is directly proportional to the square root of the tension in the string, but it's inversely proportional to the square root of the mass per unit length. Are you there? And it's also inversely proportional to the length of the string. Is that okay? By the time we combine this, F will be equal to, so provided that K is constant here F will be equal to K root T, F will be equal to K over root M, capital M. Now this one is not mass. This one is mass per unit length. So F will be equal to K over L. By the time you combine it, this thing becomes F is equal to what? 1 over L root T over M. Is this okay? And now, K over L, is that okay? So the K depends on the mode of vibration. The K depends on what? Mode of vibration. So if you say it's vibrating at fundamental frequency, K is equal to 1 over 2. In fundamental frequency. So F sub naught will become what? 1 over 2 times this becomes 1 over 2L root T over M. I've told you T is tension in string, right? L is length of wire, but M is what people usually confuse, is mass per unit length. So that's mass over what? Over length of wire. Does that make sense? All right. The last part I'll be talking about is the end correction. End correction for a pipe. End correction of a pipe. Are you tired? Yeah, don't be like my lazy student here who's already tired, not having even spent 30 minutes in the class. What? So let's go to end correction. Are you with me? Now, end correction of an open pipe is this. There are two types. We have end correction of a closed pipe. We have end correction of it. Let's start with that of a closed pipe. Now, why do we do end correction? It is called that if you set a tuning fork to vibrate on this thing, you vibrate it. The wave sent down here does not coincide with this thing, with the top of this tube. So it means that top of the tube needs a particular correction in the length. Do you understand now? So if you send a wave down here now, for example, you see that it will start vibrating. It doesn't coincide with it. Start vibrating where the wave might start from, might be around here. Do you get it? So this is the length of the wave that the wave traveled. But it means that it still needs from here to here for correction. Do you now understand? So this is what we call end correction. So for a closed pipe, so what we have is that here plus here. This place plus this place. So we have the length of the distance, wait, is going to be this C plus 1 over 4 lambda. God bless you. Does that make sense to you? So it means that the wavelength or whatever, you can just derive an equation that L minus C is equal to what? Lambda over 4. Let's call this equation 1. We can also increase it a little. If we increase it a little, we're going to have something like this too. since it's closed at one end, right? You see that the vibration will not start from the top. The vibration does not coincide with the top. So it starts from somewhere here. So it needs some end correction, isn't it? C, right? But this end from here to here is the length, right? And the length is node, antinode, node, antinode. So what would this be? 3 over 4 lambda, isn't it? So length is equal to 3 over 4 lambda. But the entire length of this thing is plus C. Does that make sense? Let's call this one L2. Let's call this one L1. Do you get it now? So what does it become? L minus C is equal to 3 over 4 lambda. Does this make sense? So what that is just saying, basically, you can just bring the equations together. If we subtract equation 1 from equation 2, for example, let's try it. Subtract equation 1 from equation 2. So equation 2 gave us equation 2 gave us L minus C is equal to 3 over 4 lambda. Subtract L minus C. This is L2, this is L1. Minus C is equal to... No. It's the same. We are using the same tube, the same pipe. So it will require the same end correction. It's equal to what here? Lambda over 4. Does this make sense? So if you subtract, let's subtract. This minus this will give us what? Quarter minus 3/4. That will be half. So that will be half lambda is equal to C minus C, 0, right? So L2 minus L1 is equal to lambda over 2. Does that make sense? And end correction is always the same. So let's prove that using an open pipe too. An open pipe. The end correction is always half wavelength. That's also true. The length of this thing, the distance between them, between each wave, each vibration you pass, is always this. Is that okay? So let's check for an open pipe. So one that is open at one end, at both ends, that is open pipe, right? In this one, there will be two end corrections, right? Isn't it? There will be two end corrections. So C and C. Then this place is length. And we know that this is antinode, node, antinode. So length is here. This length is what?
2 over L
number over 2, because it's 1 over 4, 1 over 4. Does that make sense? So it means that the entire length here is going to be C plus L1. Do you get it now?
No.
Yes, now plus L1. So the entire length will be equal to 2C plus lambda over 2. Do you get it now? Yes. L minus 2C is equal to lambda over 2. So if we now increase, let's say we increase it by 1. We have proven this, so let's clean it. Just clean this place. Is it now clear? Here, end correction 2, end correction. For this case, we have antinode, node, antinode, node, antinode. So what do we have? 1, 2, 3, 4. 4 times 1 over 4. 1, right? So length is equal to 1. God bless you, lambda. Good. So the entire length is going to be, let's call this L2. The entire length will now be C plus L2. The entire length equals to 2C plus, what is L2? Lambda. Does that make sense? So lambda equal to L minus. So equation 1 from 2. What would that give you? L minus 2C. This is L2.
L2 minus 2C plus
L2. Okay, this one should not be L2. Let's just call it L. Is that okay? Length of the distance. Is that okay? So L2 minus 2C equal to lambda. Then the other one, L minus 2C equal to lambda over 2. Subtract this, you get 0. This is L1. L2 minus L1 is equal to, subtract this from this, half again. This end correction is always, do you get it now? Alright. So that will be the end of this video. Do well to subscribe to the channel and click the bell notification. And also, I'm going to be Zabnok. I'm also going to be dropping a series of videos that will be resolved on sound waves. But I hope that at the end of this video, you'll be able to get a full grasp of sound waves. God bless you as you subscribe and share the video.